just start with a quick motivation. So I'm looking at some explanations. So I'm looking at harmonic problems in acoustics and vibroacoustics using finite element methods and boundary element methods. I usually apply a harmonic time dependence. I think it switches from time to time into between plus and minus I omega t, but I don't think this is important in this talk because it doesn't go into the details too much. What I present is often similar for vibroacoustics and vibrations of structures, but I apply to vibroacoustics and acoustics. In vibroacoustics, you have, in the frequency domain, you usually look at the solution at discrete frequencies, and then if you have a specific problem like this one with the radiated here, we called it the radiated some years ago, with a large frequency range, lots of resonances. You need a very fine frequency resolution. In that case, we had approximately 2,000 frequency steps. So that can be that can take time. Yeah. So that's why I mention here 50 solutions, 100 solutions often, and sometimes even more than 1,000. So in classical boundary value problem solutions, you look at the model with certain parameters, you do the structural analysis, the fluid analysis, you somehow couple them, so either in just one direction, so that the structure excites the fluid, but the fluid does not excite the structure. In other cases, the fluid can excite the structure as well. Then you have this feedback here. And in the end, you evaluate a certain objective function. And this is typically what mathematicians look at, or many mathematicians look at, solving the boundary value problem. But then you have this frequency loop from here to here. And then in addition, you have this feedback loop for other parameter adjustments than the frequency. So somehow you need to solve this step. So if you have 2,000 frequency steps and then another 1,000 steps for the parameter adjustments, so that can take time. And so this is usually what you have in what was it here, in optimization and uncertainty analysis. It also happens for nonlinear eigenvalue problems and diffuse field approximation. At least these many right-hand sides here with the parameter adjustments. So originally I looked at this at the problem of the reanalysis in such optimization and uncertainty problems, and I tried to reduce this presentation to the frequency loops, but you will see that there are some remainders of the other part in there. We can call it residuals. So for the example here, optimization of shell structures. So we had this mode switching all the time there. So it was not nice. So that's why I asked this. Yeah. So finding new geometries of vehicle shells here. You have a spare wheel valve. So lots of evaluations, and you have the same problem in uncertainty analysis when you solve this the problem of such a car several hundred, several thousand times. Things that like this happen. So taking this motivation, I give a short survey of my talk, and through one of the also some of the things I will try to rush through. So I start with a brief description of the math behind, so structural acoustic analysis and how the coupling is. Then I look at the assessment of vibroacoustic simulations. So what is an objective function for interior and exterior problems? Then I look at the traditional approaches for interior problems, with modal analysis again, and application of acoustic transfer vectors. Then I look at traditional approaches for exterior problems, and I see that there is no reasonable tradition. And then I go to selected methods for frequency sweeps, especially for exterior problems, but also for interior problems. And then in addition to modal superposition, low-rank approximation, and so on, I come to this parametric model auto reduction combined with Taylor and Pardee approximation. That is where I discuss this sample problem again. And I finish up with a short conclusion. So basically, the content of this talk is accommodated in this paper from 2 years ago, and some of the stuff on optimization also already in this almost 25 years old paper. Yeah. So then, my methods of simulation. So I have, in vibroacoustics, I have a simulation of a structure. So usually I take the finite element method to solve this. I have a linear system of equations, complex, yes, like this A times displacements US, so the displacements of the structure, mass matrix, damping matrix, stiffness matrix, and I have a right-hand side. Then I have a relation between displacement and velocity, and I have similar things for the fluid. If I take the finite element method for the fluid and certain infinite element formulations, I can end up with such a system of equations again, with a static mass matrix, static damping matrix, static stiffness matrix. And on the right-hand side, the particle velocity of the structure. If I take the boundary element method, I end up with these influence matrices H and G of the boundary elements. I've got a boundary admittance here and the right-hand side here. If I couple everything, I couple through coupling matrices CFS and CSF. I don't discuss them in detail, but now these equations from here and here, they are somehow coupled with these matrices, and so I've got the fluid equation on top and the structural equation below. And what we found quite reasonable in research was rearrangements via Schur complement. So I present this for the BEM equation for the fluid. So we can set up this equation, the coupled equation, just as an equation for the structure that is given here, and the H matrix here is inverted in this Schur complement, and we have an equation for the structural displacement, and the same for the fluid equation here, where we invert the structural dynamic stiffness matrix A and end up with a fluid equation for the sound pressure here. Yeah, all these matrices H, G, and A, as well as these variables, displacement, pressure, and excitation frequency, depend on the frequency. And I just mentioned that the boundary element method requires an additional post-processing for the quantities in the computational domain. I go further. Interior problems. So interior problems, if you have interior problems in acoustics, people usually look at local criteria to evaluate the results. So in industry, they usually look at, in car industry, they usually look at the sound pressure at the driver's ear. They don't talk about the left and the right, no, the left and the right ear. They just talk about the driver's ear and the sound pressure there. If you want to do it a bit better, then you look at energy density there, but still it's a local quantity, and you can end up with simple transfer functions to evaluate this, and then for these transfer functions you can easily apply Padilla approximation, what we heard before, or also. It's pretty easy, but if you have exterior problems, it's actually a bit more tricky. So usually exterior problems are evaluated based on the radiated sound power, and the radiated sound power is evaluated as an integral over sound pressure and particle velocity, and then we take just the real part. That's not so important, but we need both the sound pressure and the derivative of the sound pressure over a enveloping surface. And that can be tricky because we don't need just one transfer function. We need a lot of transfer functions. Yeah, so there are a number of simplifying evaluation techniques. Yeah, I ignored it. The problem is it's kind of a global quantity. But I come back to the interior problems. So interior problems in industry are often solved based on a modal approach. So eigenvectors of the undamped problem are evaluated, and then the modal basis is used for the frequency sweeps. That is simple, efficient, mostly correct, but the problem occurs when damping comes into play. Because this modal superposition with the modes of the undamped problem has the low damping assumption. It is often without porous material. So we heard about porous material and modal approaches before. So the frequency-dependent material is usually insufficiently represented. And the question is, what is with the modes between the resonances and so on. So that's why people came up with the idea of acoustic transfer vectors. So the idea was introduced in 1988 already by some people from Nissan, I believe, Ishiyama and Suzuki and a couple of others. And then it was reinvented a couple of times. So there's a paper on sensitivities in acoustics by Jean-Pierre Coyette from '93. There's a very similar paper by Day and a couple of others from '95. I have tried this in my doctoral thesis. Olivier, yeah, I mentioned this, and it was again reinvented in 2004 in a paper where people used it as a kind of a joint operator approach in optimization, or for sensitivity analysis actually. In 2000, this was even patented by the LMS company, and then applied to what was called SysNoise before, then Virtual Lab. Now it's called Siemens software. And yeah, I don't know whether this patent was paid out at any time. Anyway, so the idea behind these acoustic transfer vectors is such that you have the sound pressure at a certain point in a field as based on or evaluated as the scalar product of these transfer vectors or influence coefficients or whatever you call them, and the particle velocity on the surface of the structure. So just a simple sum of single products. And so that means for the fluid, you just evaluate these transfer vectors, and then you can use them for arbitrary particle velocities. So very convenient in optimization and in uncertainty quantification, because it's easy to store these acoustic transfer vectors even at 100 or 1,000 frequencies, so this doesn't matter. So as long as you have a simple, local quantity, it's quite easy to use that. Yeah, and you can evaluate panel contributions based on this. I don't talk about this in detail now. Exterior problems. So again, this equation that we had before, the sound power is the real part when you, with the surface data of the sound pressure and the particle velocity. There's a coupling matrix that's just based on geometry here, this theta. And then you can write this in terms of the particle velocity. You have the, I think it's called the Poincaré-Steklov operator here, and based on the symmetry of this operator, you can write this in this form and end up with this real symmetric impedance matrix or coupling matrix. There are different names in literature. So this coupling matrix is or has been or is frequency dependent, but it has been decomposed into eigenvalues and eigenvectors. The eigenvectors are called radiation modes, and even though the radiation modes are frequency dependent, they decay rather quickly, or the contribution decays rather quickly, and so they can be used for efficient frequency sweeps once they are evaluated, and even used in optimization as well. So there were a couple of papers in which they were used in optimization, but people probably were not so convinced of this, so this concept had never have a real breakthrough. Yeah, so, and in particular also because if you need many frequency-dependent radiation modes, then it becomes inefficient as well. There are other ideas for a modal approach, and I will talk about this later. And again, exterior problems. My idea in recent 25 years was to find an eigenvalue extraction for a modal analysis, modal superposition for exterior problems. That's why I was so interested in your first paper, Pierre. And I even mentioned it here with the absorbing boundary conditions for the to use static matrices or affine matrices in this approach. But you can have these static matrices with the SDLIs conjugated infinite elements. You can also solve a nonlinear eigenvalue problem yet without reconstruction of the harmonic solution in our case, and we had also one example with a vibro-acoustic problem, which I show later on. I will also present a quick remark on the low rank approximation scheme and on parametric modal order reduction in what follows. Yeah, and there was a recent nice paper on static matrices, or that actually two papers, no, three papers, on using perfectly matched layers with ending up with static matrices. You're smiling, Roma, yeah? Okay. Anyway, modal analysis using infinite elements. So some equations here, yeah? So these SLIs, infinite elements, are applied on an envelope of a finite element mesh around an obstacle here, shown here. And if you use this formulation with these infinite elements, you can end up with static matrices like mass matrix, damping matrix, and stiffness matrix here. You easily put this in a state space formulation and can solve the eigenvalue problem here, the generalized eigenvalue problem with matrices A and B here. And yeah, so some people don't like it because you have non-symmetric system matrices, end up with left and right eigenvectors, y and x I call them, but you can reconstruct the sound pressure based on these eigenvalues or eigenvectors, and these alphas and betas are kind of eigenvalues in this formulation. So they actually stem from the diagonalization or from the orthogonalization of these properties of these matrices A and B. And if you go further, you can evaluate the radiated sound power here based on these eigenvectors y and x, on these eigenvalues alpha and beta, and the index gamma means that for this case here, you do not need to store the values of the eigenvectors everywhere in the domain, but just on the surface. So in the end, you end up with a surface formulation based on the finite element method, like a result like in the boundary element method, which was very nice. But there's no free lunch, never. I hope for a free dinner tonight, yeah. Yeah, so the problem is it is very unclear which modes to take and how to evaluate only them. So I would even be happy with the first part here and evaluate all of them, but it's a similar problem to what you have shown, Roma. Yeah, then we have another problem. Since we have an exterior problem, exterior problems have a continuous spectrum, and if you discretize a continuous spectrum, you end up usually with spurious modes, and that was a mess in this case. So the problem was really spoiled with these spurious-like modes, and it turned out that these modes or some of these modes were required for the modal superposition. So the only thing that I could find out was that in certain examples there were really just a few modes, approximately 10 modes for a large frequency range, which provided an accuracy of 1 decibel in the radiated sound power over the whole frequency range. So the information, there was not much information in the problem, but that was needed to reconstruct the solution, but in the end it was not clear which modes to take. Yeah, so you see that this was also a problem that I considered for quite some time. My PhD students in recent years came up to the problem that they wanted to solve the nonlinear eigenvalue problem, and so I discussed this a little bit here. So it seems to be an active field of research at the moment, and the solution of the nonlinear eigenvalue problem. So it's in the boundary. Mainly investigated in the boundary element method in recent years. So there's a Chinese group by Changjun Zheng, which presented quite a number of papers on this. There were some early approaches using Taylor series polynomial approximations by Stephen Kirkup and Sia Amini many years ago. We had this in a JASA paper some 10 years ago. There were something on the Rayleigh-Ritz approach mentioned here, and some years ago we had this in a paper using the nonlinear Feast algorithm. I think that is from Shabal Fahad. And I have never found out what feast really meant. So I don't know whether anybody of you know that. But what I wanted to mention here is, if you have these modes, from these nonlinear eigenvalue problems, you lose orthogonality, but you can still use them for modal superposition. So you don't get diagonal matrices, but you just reduce everything based on the information in the modes. Yeah, so that is possible. It's not common, and I wonder if I've ever seen a paper on this. So, but it's possible at least. I think I found only this paper on mode superposition, where we solved a linearized polynomial eigenvalue problem that comes later on. So some of these normal modes, a very nice example is musical instruments. This is a recorder type fluid, and you see the first mode here and the second mode. This is the first and this is the second, so with sound pressure in color, and this is for another tone, first and second mode. You see the openings of this recorder type fluid here. Or eigenvalues and eigenvectors for a sonic crystal are shown here. So nice pictures, very difficult to interpret. Yeah, but one thing that you can see here, I need to check this in detail. Hang on. So if you look at these modes here, so you see them, they are very localized. These are really, there's really low damping here. You see this in the eigenvalue here. Very low damping also here. So these modes are almost like bound states in the continuum, with hardly any interaction with outside. Nice results, as I said, difficult to interpret. Then this eigenvalue problem, or this eigenvalue problem and modal superposition of the coupled problem, the vibro-acoustic problem, where we rearranged it with the Schur complement and then developed the Poincaré-Steklov operator, or we call it in acoustics impedance matrix, into a series up to order 6 or order 8. So we did both. So it became a large eigenvalue problem for which we used in an Arnoldi algorithm to reduce that again. So that is described in this paper here in JASA from 12 years ago. Yeah, and then this the work on the nonlinear eigenvalue problems. I think you will distribute the presentation anyway later on, yeah. So you can read it there. Yeah, so this is that's serious. I'm hungry, yeah. And so once again, this the solution of this eigenvalue problem of the vibroacoustic problem here. We had this in the model. We had this shell structure with finite elements and the boundary element measure of this shell structure and coupled them, and we looked at the different modes and modal superposition, and what we can see here is where we grouped the modes and their contribution to the radiated sound power, and so you can hardly see this gray stuff here with this radiated sound power, but this blue curve are just the breathing modes. There were quite a number of these breathing modes, and so they have dominated a certain load case, which is shown here. In other cases, the bending modes, that is grouped in the zero modes here, and all the higher order modes were not really relevant for this example. And we even applied a modal superposition there, and that gave us speed-ups of amazing 99% or so. But the offline part was quite expensive, yeah. Anyway, so go further. Nonlinear eigenvalue problems and even mode superposition here for the evaluation of where is it? Of radiation damping. Shown here for this plate and explained in this JASA paper from 2020. So the interesting part here was that the radiation damping of lightweight material is often the dominating part of the damping. So you see more than 2% damping in a higher frequency range. So I mentioned this low-rank approximation scheme. So it somehow worked, is explained in this paper. It's also open access here, Journal of Theoretical and Computational Acoustics. A very nice journal. Yeah, and we made it open access there, even in that journal. And more recently, we had this application of Gaussian processes for frequency sweeps, and that is explained in the JASA paper here by Chala Goebitz and a couple of others. Now this what we had before. You see, there's a lot of names, or there are a lot of names here. I think on the boundary element method, the first paper on Padé approximation was by Jean-Pierre Coyette and a couple of co-workers in '99. Modal order reduction and Padé approximation, that is what I believe was first introduced by Roland Freund. Do you agree, Romain? Very convincing, yeah. And in acoustics, from my point of view, by Manish Malhotra and Peter Pinsky about 25 years ago. In Padé, presenting the Padé-Vialanchas method, actually developed by Roland Freund, but applied to acoustics by Malhotra and Pinsky. There was lots of work later on, yeah. So Peter Pinsky with Markus Wagner, then James Tuck-Lee on matrix Padevia-Lanchos. Chabel Fahad did a lot of basic work there. An implementation to ANSYS was presented by Yevgeny Rudny about 20 years ago. A couple of nice papers on Arnoldi methods by Srini Puri and Dennis More. Then we have the 3D, yeah, Deckers, Desmet, and Dionysius. The Löwen group, yeah. Sorry, no, Olivier. No. But yeah, but your name is too long. So look at Wim and Elke, 7 letters on 2 names. Yeah. So anyway, so I mentioned the 3D from Löwen with lots of papers over the recent decade. Romain, Kirin Aumann, and that is from your group. Yeah, Kirin was in your group. I mentioned him because he had a paper with Steffen Werner, and you were not on that paper, so I had to save space here because there were so many papers. Then we have Chan Shi and Jijun Liu, and a couple of papers from our team in this field, and still a number of others. I would call it an extreme active field of research, and that's why we are here. 10 doctoral students, yeah, 10 in just working on that, basically working on that field. Yeah. Anyway, so I will go through very quickly with that one. So our development was that on the greedy algorithm. So the nice thing of that greedy algorithm is that it is so simple. So it is just 6 lines, and that is the whole algorithm. So anybody who is interested in can read it and program it from here. But what I learned from Dionysius, or what Dionysius told me, was that we still need to do the whole system of equations to sample. The good thing that I really enjoyed in this algorithm is that we can reduce automatically, or we can sample automatically, because we don't need to a priori define where we want to sample, and it's explained here. No, this is not. So explained here. So we look at this example, that a duct, again, we have every 50 hertz, we have a resonance here. When we look at the convergence here, with just one sampling at one point, we have more or less 100% error over frequency. And then with a few samples, 10 samples, we reduce the error down to 10 to the minus of 5. It's actually not the error, it's the residual, but we assume it's close to the error. Yeah. And the same in double sweep. So one sweep over frequency and the other sweep over the Young's modulus of a submerged steel sphere. And in that case, the whole picture is based on almost 1,000 evaluations, but using this greedy algorithm in 2D, we decrease the error down to looking at this, probably 10 to the minus 5, not with 20, but 25 iterations approximately. And that brings me to my concluding remarks. So I guess you will remember most of the parts. So I tried to give some concepts and approaches on frequency sweeps, and originally in that paper with many right-hand sides. So it's simple and straightforward for interior problem. Exterior problems are a bit more demanding. I presented something on modal analysis, low-rank schemes, parametric modal auto reductions, and so on. So yeah, all these things that might be more interesting to see who is acknowledged. Not the Vamo project, but it's internal. So I would like to acknowledge my own team here, which contributed a lot. My collaborators in Australia, my collaborators in China, and some others. And here's the one of this or two of this of the 3Ds, and also Markus Wagner and Bert Rosen. And that brings me to the end of my talk. Yeah, so basically the most important picture here. Thank you very much.